So here we start to explore vector multiplication. But before we dive into it, we have to understand the difference between a vector, something that has magnitude and direction, like wind or the movement of a car, versus a scalar. So a scalar is a quantity that has magnitude but no direction. So we can think of that as something like time, although of course time always marches forward. It doesn't actually have a direction. Volume is another example of a scalar, something that does not have direction. It does not matter how a box is oriented, its volume is still the same. Now, when we multiply a vector by a constant, we're essentially multiplying a vector by a scalar. And so that is possible. We can also have a vector multiply another vector, but because vectors have both magnitude and direction, we can't just multiply the numbers and be done with it. It's a little bit different. And so there's actually three different types of vector multiplication that are defined. The first is the simplest. So this is where we're multiplying a vector by a scalar. And so the end result is you just end up with another vector. So if I multiply a vector by 2, a scalar of 2, it just means that my vector now is going to have double the magnitude, but it's going to have the same orientation. If we multiply by a negative value, then it's going to reverse the direction of the vector and then change the magnitude by whatever number we multiply. Second is what we're going to be focused on today, which is multiplication of a vector by another vector to yield a scalar. So you can actually multiply two things that have both magnitude and direction, two vectors, and end up with just a number. You just end up with a scalar. And then later on, not today, but in our next lesson, we're going to take a look at what's called the cross product, where you multiply two vectors together and end up with another vector. So first we have examples of that simplest type of vector multiplication where we multiply a vector by a scalar. So if we have our initial vector a right here, if we have 2 times a, then you can see that we end up with just double the length, but the orientation of the vector is the same. If we multiply by -2, then we just have double the magnitude, double the length, but now we've reversed the direction of that vector. But when we multiply a vector by another vector, that's where things get a little bit more complicated. And so, like I mentioned earlier, there are two types of vector multiplication that are defined, and the one that produces a scalar is what we call the dot product. And so there are actually two different ways that we can calculate the dot product of two vectors. And so the first of those is to take the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle in between them. And that angle will always be the short distance between them. So it'll always be less than 180 degrees. And so we can see that this indeed will produce a scalar. Magnitude is just a number. Magnitude of b is just a number. Cosine of an angle gives us just a number. So we're just multiplying three numbers together. So we are indeed going to end up with a scalar when we're all done, which is a bit curious that we're going to multiply two quantities that have both magnitude and direction and yet end up with just a number. But this is one type of vector multiplication that's defined for us. Now, there is a second method of calculating the dot product, and usually we'll use these in concert with one another, as we'll see in our examples later. But what we can tell from this formula here is that if the angle between two vectors is 0, so let's say the two vectors are oriented in the same direction, then the dot product is going to be just the product of the magnitudes of the two vectors, because the cosine of 0 is 1. If the angle between them is acute, it means the dot product is just going to be some positive number, because cosine is positive in the first quadrant. Interestingly, if we get a dot product of 0, that means that the vectors are perpendicular to each other, because the cosine of 90 is 0. And then finally, if we have an angle that's bigger than 180 degrees, something between 90 and bigger than 90 degrees, something between 90 and 180, the angle is obtuse, then we know the dot product is going to turn out to be negative, because cosine is negative in the second quadrant. So let's use that formula to find the dot product between the two vectors that are given here. So we have vector A and vector B. So I'm going to sketch those on a coordinate plane for ourselves. So for the vector A, I have 6 as my I component, so 6 in the horizontal direction and negative 6 root 3 in the J. So we're looking at something like this. So here's 6 root 3 in that negative direction. Now hopefully that jumps out at us as being a 30, 60, 90 triangle, where this angle here is 60 degrees. And that's going to matter to us because in that formula for the dot product, it's going to be the magnitude of A times the magnitude of B times the cosine of the angle between them. So we've got to make sure that we figure out what the angle between these is, so knowing that that 60 degrees there may be useful to us. Second, now we've got the vector B, so negative 4 root 3 and then positive 4. So we're looking at something maybe like this. So if I drop it perpendicular, we've got negative 4 root 3 here, make that negative there, and then 4 in the vertical direction, another 30, 60, 90 triangle. So we know that this angle right here is 30 degrees. So taken together, we can see that the angle between these two vectors, we have to go the short way. So this angle here is 30, if the other piece of that one is 60. Then we have a 90-degree angle here, and then we have another 30 degrees right here. So taken together, 30 plus 90 plus 30. So our angle between these vectors is going to be 150 degrees. So now that we know the angle, again a reminder, we need the two magnitudes of the vectors times the cosine of that angle. Well, the magnitude of the vector A, again because it's a 30, 60, 90 triangle, that's going to be 12, so double the short leg. Same thing's going to be true for the other triangle that we have here. So the short leg is 4, so that means the magnitude of the second vector is 8. So we're looking at 12 times 8 times the cosine of 150, or 12 times 8 times negative root 3 over 2. And so then we can either write our answer as negative 48 root 3 once we simplify that expression, or if we want to use our 3 decimal place standard that we've been using for many calculations so far, we've got negative 83.1. Now that number taken by itself doesn't have a whole lot of meaning. It's not like I look at a result of negative 83.1 and say, ah, that tells me something about the two vectors, other than because I have a negative value for the dot product, that confirms for me that my angle is indeed obtuse, but that's what I plugged into the formula. But what we do is we use this formula in concert with a second version of the dot product formula to actually calculate the angle given other information about our vector, as we'll see in our other example.